Okay. Hi. Today I want to talk a little bit about things that aren't quite categories. And I thought that as a decent warm-up, we could talk about things that are categories and that have sets as their objects, but don't necessarily have functions for their arrows. And I thought that this might be an interesting introduction to the idea that not everything is the category of sets and functions. First, let's look at things that are subcategories of our familiar category. Note that in order to have a category, we really only need two principles of functions. The first principle of functions is if you have any set, there's an identity function. That's useful. And second, there's composition, right? If you have two arrows that line up, one arrow has a target set that is the source set of another arrow, then you can compose them. So there are subclasses of functions that have this property. The identity arrows themselves, and also injections, and surjections, and finally bijections all have this property. So there are correspondingly categories of sets and injections, sets and surjections, right? There are a few interesting things about these categories. The first interesting thing is that the category of sets and injections has monomorphisms for every arrow. And you can think of a monomorphism as a subset or a sub-object, right? So the category of sets and injections is a category of sub-objects, which is an interesting situation. The category of sets and bijections, since every bijection has an inverse, this creates a groupoid structure. So this category is a groupoid. That's it for these subcategories. As for supercategories, I suppose, right? Functions are a special case of several situations. One important case is that the category of sets and partial functions is a supercategory. So every total function can be interpreted as a partial function, but not every partial function is total. There are useful computational properties associated with this category. Hi, friend. There are useful computational properties associated with this category. One important idea is that partiality can correspond to failure. It can also correspond to diagonalization or incompleteness. We can also view this as equivalent to a category whose objects are not just sets, but sets with specified base points. And these base points indicate partiality or failure. We require then that mappings preserve this, partiality to partiality. But this turns out to correspond to the category of sets and partial functions exactly. Finally, there is a general structure of sets and relations. So this category has many desirable properties. The biggest one is that it's a dagger category, right? So for every relation between two sets, we have a corresponding relation which is just the same relation but backwards. And because we're allowed to do that for every relation, we're allowed to turn the entire category around. This is kind of like being a groupoid, but even more so. One of the really, really interesting parts of category theory is that we can use the fact that there are different categories with the same objects but different arrows to create what are called double categories. And all I'll say about those today is that these are categories where there's one type of object, but there are two types of arrows. So there's a double category whose objects are sets and whose first type of arrows are functions, but whose second type of arrows are partial functions. There's also a double category whose objects are sets and whose first type of arrows are functions, but whose second type of arrows are relations. And the resulting categorical structure that comes from elaborating this and figuring out the definition is something that I don't think we really ever would understand if we insisted that there were only one type of arrow for each particular type of object. At any rate, that's all that I've got for you today. Sorry for the bright light. It is the beginning of spring. I will see you all later.